Hello viewers, welcome to my channel. In the present class, we are going to discuss the topic thermodynamic potentials and Maxwell equations. Thermodynamic potentials and Maxwell equations. So what are the thermodynamic variables? First, let us see. To describe the thermodynamic system, to describe any thermodynamic system, we require some quantities, physical quantities, such as pressure, volume, temperature, entropy. These physical quantities are called as thermodynamic variables. Thermodynamic variables. To describe any thermodynamical system, the physical quantities required are called as thermodynamic variables. So we use pressure, volume, temperature, entropy. So we describe any thermodynamic system in terms of these four quantities. Pressure denoted with the P, volume denoted with the V, temperature, absolute temperature is denoted by the letter capital T, and entropy capital S. Okay, sir. So the next, what is thermodynamic equation? What is meant by thermodynamic equation? So the mathematical equation which explains in detail about a thermodynamic system is called as thermodynamic state equation. Thermodynamic state equation. Okay. For example, if you take ideal gas, PV is equal to RT. For 1 mole of gas, any ideal gas obeys the equation P into V is equal to RT. Am I right? What is
Yes,
the
sir.
ideal gas equation? P into V is equal to capital RT, where P stands for pressure, V stands for volume, capital T absolute temperature, or universal gas constant. When we talk about real gas or van der Waals gas, that is explained by the van der Waals equation, P plus A by V square into V minus B, V minus B is equal to RT. This is the van der Waals equation. All the real gases obeys this equation. So when we describe a real gas in the container, a thermodynamic system of real gas, simply we explain by using this equation, P plus A by V square into V minus B equal to RT. In this equation, again, P pressure, V volume, capital T absolute temperature, right, or universal gas constant, A and B are van der Waals constants. Van der Waals constants. So what I'm saying is here, a mathematical equation which explains the state of thermodynamic system is called as thermodynamic state equation. Thermodynamic state equation. Okay. Now, so this is one thing. So what are the thermodynamic potentials? Thermodynamic variables are different from thermodynamic potentials. Okay, sir. Thermodynamic potentials are four. Thermodynamic potentials are four physical quantities. One is internal energy. It is denoted with the letter capital U. Enthalpy. It is denoted with the letter H. Free Helmholtz energy. It is denoted with the letter capital F. And the Gibbs free energy. It is denoted by the letter capital C. Internal energy, enthalpy, free Helmholtz energy, and Gibbs free energy. Gibbs free energy. So by using these four scalar functions, all these are the energy functions. Internal energy is the energy function. It is there. The term is there. Enthalpy is also, this is also form of energy. Free Helmholtz energy. So that also we are using the term energy. It gives free energy. That also the energy term. Energy, internal energy, enthalpy, free Helmholtz energy, and Gibbs free energy. These four physical quantities are energy functions. These are all scalar functions, right? The energy functions are the scalar functions which describes the thermodynamic system completely are called as thermodynamic potentials. So they are, one is internal energy, the second one enthalpy, the third one free Helmholtz energy, the fourth one gives free energy. Clear, sir? Okay, right.
Yes, sir.
Yeah. Now, let us discuss in detail about these four thermodynamic potentials. First, let us see what is internal energy. Internal energy. When we talk about a gaseous system in the container or vessel, gas is nothing but that is a composing of a very large number of molecules. Comparing to the solids and liquids, gas molecules are very distant. They move randomly in all directions. We discussed in kinetic theory of gases. The gas molecules move randomly, so they can collide with another molecule or with the walls of the vessel. So they undergoes to the elastic collisions, right? So all these things, so you should keep in your mind, right, sir? Here the molecule is moving. The molecule is displacing from one position to another position, right? Since the molecule is in the motion, it possesses the kinetic energy. And also there exist intermolecular attraction forces among the molecules. So one molecule can attracted by another molecule, surrounding molecule, or neighbor molecule. So between the neighbor molecule, there exists some intermolecular attraction forces. Because of that intermolecular forces, the potential energy exists. They possess the potential energy. Because of the molecular motion, they are having the kinetic energy. So here the molecule is having two types of energies. One is the kinetic energy, the second one potential energy. The sum of kinetic energy and potential energy gives the internal energy of the system. But strictly speaking, in addition to this kinetic energy and potential energy, there are some other forms of energy, because the molecule can have the oscillatory motion. Because in any solids, liquids, or here the molecule will have the vibratory motion, oscillatory motion. So therefore, there exists some vibrational energy. Yeah, the molecule may rotate with respect to x-axis or y-axis or z-axis, just like a rigid body dynamics, what we are discussing in the first sem. The gas molecule you can assume as the rigid body, rigid sphere. So that can have the rotatory motion. So because of that, it has the rotational energy. Because of the vibrational motion, it may have the vibrational energy, right? In general, the molecule is moving randomly throughout the volume of the vessel. Therefore, it is having the kinetic energy. Because of the molecular attraction forces, it is having the potential energy. So, kinetic energy, potential energy, vibrational energy, and rotational energy. The sum of kinetic energy, potential energy, vibrational energy, and rotational energy, that gives the total internal energy of the system. It is denoted by the letter U, right? So comparing to the kinetic energy, internal kinetic energy. So kinetic energy is also known as internal kinetic energy. In here, kinetic energy and the potential energy for contribution is small. So comparing to the kinetic energy and potential energy, we can neglect the vibrational energy and rotational energy. So that's why simply we define internal energy as the sum of internal kinetic energy and internal potential energy. Okay, so internal energy of the system U is equal to internal kinetic energy, that is UK, plus internal potential energy UP. Right, sir. If the internal energy of the system increases, its temperature increases. If the internal energy of the system decreases, temperature of the thermal system decreases. So that's why internal energy is the function of temperature or vice versa. Our temperature is the function of internal energy. If the internal energy is more, the temperature of the system will be more. If the internal energy of the system is less, the temperature of the system will be less. Okay, sir. U is equal to UK plus UP, right? UK is internal kinetic energy, UP is internal potential energy. If there is a more internal energy, temperature of the system will be more. If there is a less internal energy, temperature of the system will be less. Therefore, temperature depends on internal energy. So this is very, very important point. We use this term throughout this all chapters. So that is about internal energy. The second concept is enthalpy. So what is enthalpy? Enthalpy is defined as this is sum of internal energy and the product of pressure and volume. H is equal to U plus PV. H equal to U plus PV. Pressure into volume. Pressure into volume also energy function. U already we discussed, it is the energy, internal energy. So internal energy plus PV. PV also represents the energy function. Hence, H is the energy function. H is defined as it is the sum of internal energy and the product of pressure and volume. Clear, sir? Right. The third one is free Helmholtz energy. The third scalar energy function or thermodynamic potential, that is free Helmholtz energy. So F is equal to here U minus Ts. F is equal to U minus Ts. How we are defining? F is equal to that is I'm writing here. Let's write. F equal to this is defined as internal energy minus T, the product of temperature and entropy. S is entropy. Okay. The fourth one gives free energy. It is given by H minus Ts. It is given by H minus Ts. H enthalpy minus the product of temperature into entropy. So four thermodynamic potentials we define. Internal energy U equal to UK plus UP. The second thermodynamic potential enthalpy, it is given by mathematically expressed as H is equal to U plus PV. The third thermodynamic potential Helmholtz free energy, F is equal to U minus Ts, and Gibbs free energy expressed as capital G is equal to H minus Ts. So how we are defining? The thermodynamic functions or potentials which are formed by combining the four thermodynamic variables. These are the energy functions which are used for the complete description of the thermodynamic system. So all these parameters we write in terms of thermodynamic variables. So what are thermodynamic variables? I told you: pressure, volume, temperature, entropy. For example, you take H is equal to U plus P. H is equal to U plus P, where U, pressure, volume, that is the thermodynamic variable. F is equal to U minus Ts. F is expressed in terms of internal energy, temperature, and entropy. And G equal to H minus Ts. There also G is expressed in terms of HTS. G is equal to H minus Ts. We convert into terms of pressure, volume, temperature. Yes, sir. Each function we convert or we express in terms of only these four quantities: pressure, volume, temperature, entropy. Okay. So from that, we derive the equations, the differential equations, first order differential equations. They are called as Maxwell thermodynamic relations. So by using these four thermodynamic potentials, we derive the four equations. So Maxwell derived four differential equations to describe any thermodynamic system. Those equations are said to be Maxwell thermodynamic equations or Maxwell thermodynamic relations. Okay, I hope you understand. Now, so let us derive the Maxwell equations. First, we take the first law of thermodynamics. First law of thermodynamics you studied at your intermediate level. What is that mathematical expression? dq is equal to du plus dw. So once again, I will repeat this concept. The first law of thermodynamics states that when some amount of heat energy dq is given to the system, that is utilized in the two ways. Some part of energy is used to increase the internal energy. The remaining part of energy is used in the external work done. Right? The increased internal energy is du. external work done is TW. For example, I'm explaining by means of the figure. So this is a cylinder with the piston. In this, we have taken some ideal gas. From outside, I'm heating. I'm giving some heat energy dq, right, sir? So some dq energy is given to the thermodynamic system. So to the gaseous system inside the cylinder. So then, so whatever the energy given to the system, it is utilized for the two ways. Some part of energy is used to increase the temperature of the gas. That means internal energy. Some part of energy is used for internal energy or to increase the temperature of the gas. And this piston will move outside. So here the gas expands. Because of the gas expands, the piston will move outside. So this is the piston is displaced here. That is also we use in other term external work done, because the piston is displacing because of the force pressure of the gas. The piston is moving outside. Here some work done by the system, work done by the gaseous system. Therefore some energy is used for external work done. Hence what we are stating, dq is utilized in the two ways. Some part of energy is used for du. The remaining part of energy is used as external work done or in the expansion of the gas. Hence, mathematically, we express it as dq equal to du plus dw. But dw equal to p into dv, pressure into change in volume. Therefore, the first law of thermodynamics expression dq is equal to du plus dw or dq equal to du plus pdv, because their dw equal to pdv, right, sir? So this is the first law of thermodynamics mathematical expression. And the second law of thermodynamics mathematical expression, it is also you studied in intermediate second year, first year, dq equal to tds. dq equal to tds. When dq energy is given to the system, then what happens? The molecules take that receives that thermal energy. The molecular random motion increases. Okay, entropy is nothing but it is the measurement. It is the measure of randomness of the system. Okay, the molecules randomness increases. We say that entropy is increasing. If the molecular random motion decreased, we say that the entropy decreased. So when we are supplying some amount of heat energy to the system, since they receive the thermal energy, their vigorous motion increases, random motion increases, and the collisions increases, the molecule motion increases, and entropy increases. So ds is change in entropy. ds is change in entropy. Second law of thermodynamics talks about entropy concept. dq equal to t into ds. This is the equation 1, equation 2. Actually, all these things we discuss in the thermodynamics chapter. Because of these are the basic concept, I started directly in thermodynamic potentials and Maxwell equations. You don't bother about, because these are all fundamental things. dq equal to du plus pdv from first law of thermodynamics. dq equal tds from second law of thermodynamics. You should remember these two. By combining these two equations, we can write TDS is equal to du plus PD. From that, du equal to TDS minus PD. Okay, du equal to TDS minus PD. So here, differentiate that equation. With respect to S. du equal to TDS minus PdV. So differentiate this equation with respect S at constant volume. So then left side, what you get? Dou u by dou S. Dou u by dou S at constant volume. So dou u by dou S, then you will get T, because at constant volume, dV equal to 0. Are you getting my point, sir? At constant volume, change in volume dV equal to 0, because V constant, dV equal to 0. Then you can write dou u by dou S is equal to T. Similarly, you differentiate this equation with respect to volume at constant entropy. At constant entropy, S constant, then ds is equal to 0. Then you will get du equal minus PdV. So dou u by dou v over s is equal to minus p. Clear, sir? Have you followed? Dou
Yes.
u by dou s at constant v is equal to t. Dou u by dou v at constant s is equal to minus p. Since du is a perfect differential, we can write dou by dou v of dou u by dou s is equal dou by dou s of dou u by dou v. That means dou square u by dou v dou s is equal dou square u by dou v dou s, or dou square u by dou x dou y equal dou square u by dou y dou x. When okay, du is the perfect differential, right? So from partial differentiation theorems, we have the concept that dou square u by dou x dou y equal to dou square u by dou y dou x. So according to that here, dou square u by dou v dou s is equal dou square u by dou s dou v. So therefore, you take this one, dou by dou v of dou u by dou s over v is equal dou by dou s of dou u by dou y over s. But dou u by dou s at constant p, what we get? T. Then dou t by dou v over s is equal, here left side, dou by dou s of dou u by dou v. Dou u by dou v over s is equal to minus p. Therefore, right side you will get, what you get? Wait for 1 minute. Yes, sir. Yes, the screen is visible.
Yes, sir.
Yeah. So dou by dou v, dou u by dou s over v, we got t. Hence dou t by dou v. Right side, dou by dou s of dou u by dou v. Dou u by dou v, what is dou u by dou v? That is minus p. Minus p. Okay. Hence minus dou p by dou s. So you write s here, you write v here. Therefore, finally, here we got the equation dou t by dou v over s is equal minus dou p by dou s over v. This is the Maxwell first thermodynamic relation. Maxwell first thermodynamic relation is dou t by dou v over s. So whatever we are writing over the bracket, okay, as a subscript, so that means that is constant there. Dou t by dou v at constant s is equal. So we read it as minus dou p by dou s at constant volume. So this equation is called as Maxwell first thermodynamic relation. Clear, sir? Now, so how we derived, let me repeat. Just simply you take first law of thermodynamics, dq equal to u plus dw, or dq equal to u plus pdv, equation 1. Next, you take the mathematical expression of second law of thermodynamics, dq equal to tds, equation 2. Combining these two equations, we have written tds is equal to du plus pdv. So from that, we are taking the differentiation, and since the du is perfect differential, we have written dou by dou v of dou u by dou s is equal dou by dou s of dou u by dou v. From that, we got dou t by dou v over s is equal minus dou p by dou s over v. So this is the Maxwell first thermodynamic relation. Okay, now, so let us derive the second thermodynamic relation. So for that, you take the enthalpy concept. So how we define enthalpy? Enthalpy also some energy function, thermodynamic scalar function. It is defined as the sum of internal energy and the product of pressure and volume. H is equal to U plus PV. So that equation, you differentiate both sides, then you will get dH is equal to du plus P constant P into dV plus V constant V into dV. Okay, what I am saying, H is equal to U plus PV. This is equation 1. Simply we differentiating both sides. Then dH is equal du plus PdV plus VdP. But according to the concept, whatever we discussed in the previous Maxwell equation, there we got du equal TdS minus PdV. So we got this equation by combining the first law of thermodynamics and second law of thermodynamics. So now simply you substitute to, instead of du equal to TdS minus PdV, substitute in this equation. Then what we get, dH is equal TdS minus PdV plus PdV plus VdP. Am I right, sir? Minus VdV plus PdV cancel now. Okay. So then what left? dH is equal to TdS plus VdP. This is equation 2. So this is the required expression. If you got this expression, you can write the Maxwell second illusion. Okay. To write the Maxwell first equation, we use this one, du equal TdS minus PdV. This is the required equation there. So for the second Maxwell equation, whatever the expression we require is dH is equal TdS plus VdP. Right. So after getting this expression, so what you have to do is, now dou H by dou S at constant P. When the pressure is constant, then dP 0, then VdP term becomes 0, then dou H by dou S is equal to T. Therefore, dou H by dou S. So we can write dou H, that is change in enthalpy. Dou H by dou S with respect to entropy. Dou H by dou S at constant pressure. Dou H by dou S at constant P is equal to T, because dP 0. Similarly, at constant entropy, when entropy is constant, ds is equal to 0, then we get dou H by dou P, at constant S is equal to, Vd. When S is constant, ds is 0, first term becomes 0. Following, this is 0. Then dH is equal to VdP. So dou H by dou P is equal to V. Right, sir? Again, here dH is also perfect differential. When this perfect differential, applying that perfect differential concept, dou by dou P of dou H by dou S is equal to dou by dou S of dou H by dou P. That means dou square H by dou P dou S is equal to dou square H by dou P dou S. So therefore here already we have dou H by dou S. Therefore left side you take dou by dou P. Here dou H by dou P. Hence left side you take dou by dou S. Right, sir? Then we can write the expression right. Okay. So dH is equal to TdS plus VdP. Dou H by dou S at constant P equal to T, that is written. Dou H by dou P at constant S is equal to V. Then dou by dou P of dou H by dou S at constant P equal dou by dou S of dou H by dou P at constant. But dou H by dou S at constant P, T cell. So that is substituted here. Dou T by dou P at constant. That equal dou by dou S of this. So but this is equal to V. Hence dou V by dou S at constant P. This is Maxwell's second thermodynamic relation. Dou T by dou P at constant S is equal dou V by dou S at constant P. This is called Maxwell second thermodynamic relations. Clear, sir? Now, so the third relation, what is the Maxwell third relation? So for that, you take Helmholtz free energy. F is equal to U minus Ts. F equal to U minus Ts concept you take. You differentiate that both sides. F is equal to U minus Ts. You differentiate both sides. Then you will get dF is equal du minus TdS minus STT. But du equal TdS minus PdV. You substitute there. dF equal TdS minus PdV minus TdS minus STT. Minus TdS plus TdS cancel. Then dF equal minus PdV minus STC. So this is a required expression to write the Maxwell third thermodynamic relation. Again here at constant temperature dt 0, then df equal minus p dv, dou f by dou v constant equal to minus p will get. At constant volume v constant, then dv equal to 0, then you will get df equal minus sdt. So then df dou f by dou t equal to minus s. Again, df is the perfect differential equation. Then dou square f by dou v, dou square f by s, dou v dou t equal dou square f by dou t dou v. Using this concept, we will get the third thermodynamic relation. So that is how we are writing. Let us say, yeah, dou f by dou v at t equal to minus t, dou f by dou t at constant v equal to minus s. Since the df is perfect differential, dou by dou t of dou f by dou v equal dou by dou v of dou f by dou t. Okay, sir. Then dou f by dou v at constant t, we have the minus p. Therefore, left side we get minus dou p by dou t at constant v equal right side dou by dou v of dou f by dou t. Dou f by dou t at constant v, we have minus s, hence it will be minus the dou s by dou v at constant. Both sides minus minus cancel. Then finally, we will have the equation dou p by dou t at constant v equal dou s by dou v at constant t. So this is the Maxwell third thermodynamic relation. Dou p by dou t over v equal